Hello, thanks for your interest in this work. My name is Renji Li. In this talk, I'm going to show you some fundamental limits of mobility management today and how to reduce its failures by an order of magnitude in extreme mobility. Extreme mobility has been a norm rather than an exception. Every day, we enjoy life convenience from high-speed trains, vehicles, and drones. Compared to the static and low mobility scenarios, extreme mobility involves much faster client movement in the wild environment. Many extreme mobility scenarios need always-on internet access anywhere, anytime. Today, a common solution is a mobile network, such as 4G LTE, 5G, and even beyond. It is the only wireless infrastructure that offers wide area mobility management for network access. It has served billions of users and will hopefully serve trillions of Internet of Things. Let's look at how 4G and 5G supports mobility today. To enable anywhere, anytime network access, 4G and 5G deploy radio base stations to cover different geographic areas. Each base station may run multiple cells on the various frequency bands with different radio coverage and performance. As the client leaves one cell's coverage, it will be migrated to another one to retain its network access. This is called handover. The handover today is mainly driven by the wireless qualities. It has three phases. In the triggering phase, the serving cell configures the client to measure the neighboring cell's wireless quality. Once the client sends the feedback, the serving cell moves to decision phase. In 4G and 5G, each cell can customize its own handover decision policy to accommodate diverse demands, such as fast network access, good radio quality, load balancing, and etc. The serving cell runs this local policy to decide if more feedback is needed, if handover should start, and which cells the client should move to. This local policy can be viewed as a finite machine, and it could be very complex in reality. We'll get back to it later. After a handover decision, the serving cell moves to the execution phase by sending the handover command to the client. Then the client will disconnect from the serving cell and connect to a new target cell. So in summary, the mobility management today takes wireless quality as input, relies on the client side wireless feedback, and decides the target cell based on the local wireless-driven policy. As you can tell, the mobility management should be reliable enough to guarantee the seamless internet. This is very important for many emergent scenarios, such as safe self-driving cars, industrial IoT, mission-critical communications, and many more. But is it really reliable? Although successful for static and low mobility scenarios today, 4G and 5G mobility management are not really reliable in extreme mobility. We have conducted a large-scale empirical study of 4G LTE over Chinese high-speed rails. On one hand, the handovers are more frequent in extreme mobility. It happens every 11 to 20 seconds, depending on how fast the client moves. But on the other hand, different from static or low mobility scenarios, handover failures and policy conflicts arise with alarming frequency in extreme mobility. The failure ratio increases from 5% to 12% as the client moves faster and faster. That means every 3 minutes, we will experience a network failure on a high-speed train. Note that most of the failures are not caused by radio coverage holes. Instead, they are caused by the fundamental limit of mobility management design today. Although these results are from 4G LTE, the 5G's reliability could be more challenging because of its more frequent handovers between small cells and higher 5G radio frequency. So why are 4G and 5G unreliable in extreme mobility? The fundamental problem is its wireless-driven mobility management design. As the client moves, the wireless signal propagation path also changes and results in wireless dynamics. This is called multipath fading. The client movement also causes Doppler frequency shift and results in the interference between cells and wireless quality degradation. The communication theory tells us that the wireless channel remains approximately invariant in a very short duration. This is quantified by the coherence time, which is inversely proportional to the Doppler shift. The Doppler shift is proportional to the client's movement and radio frequency. In static and low mobility scenarios, the multipath fading and Doppler effect is negligible, so the channel coherence is reasonably long. But in extreme mobility, a fast-moving client on the higher radio frequency will experience much more dramatic change dynamics. With such dynamics, the handover signaling can be easily lost or corrupted over the air, which results in the handover failures. In Chinese high-speed rails, 19 to 30% of handover failures come from the handover command signal loss. During these failures, the average radio block error rate is up to 30% for downlink and 9% for uplink. Even worse, such worse dynamics will propagate failures to all phases of the mobility management. We have seen that it will cause unreliable signaling in the handover execution. Besides that, the triggering and decision phases are also affected. At the triggering phase, such voice-based feedback can be sluggish and cause failures. To have a successful handover, the client should deliver its feedback before it leaves the serving cell's coverage. But in reality, the client may not be able to do so for two reasons. First, to make a proper handover decision, the client should measure all candidate cells around. For wireless quality-based feedback, this client has to measure them sequentially, thus delaying later cells feedback. Although we could reduce the cells to explore so that we can reduce latency, this would be at the risk of missing available cells and causing out-of-service failures. Second, as we have seen, the word quality fluctuates dramatically. So this would cause transient handover oscillations between cells. To mitigate them, 4G and 5G mandate the client to send feedback only if a cell meets triggering criteria for a configurable timer interval. In reality, this timer usually ranges between 40 to 640 milliseconds, and the timer will delay the feedback and cause late handover failures. Our study has shown that a client on Chinese high-speed rails takes about 800 milliseconds on average to generate feedback of all cells. But during this period, the client itself has moved 78 meters along the rails, so it's too late for a minimal handover. The fundamental problem is that in extreme mobility, the wireless feedback faces the exploration versus exploration dilemma. The client has to choose between either it does more measurements for proper handover or it does fast feedback for timely handover. Then let's look at the decision phase. In this phase, the mobility management suffers from a complex decision policy. To improve the radio coverage and performance, the mobile network operators deploy multiple cells under different frequency bands. To tackle these heterogeneous cells, most operators adopt multi-stage handover policies. The neighbor cells under the same frequency as the serving cells are measured and selected first. Only if no intra-frequency cells exist and the serving cells too weak, then the policy will consider the inter-frequency cells through the measurement reconfiguration. The reason is that inter-frequency measurements will cost more spectrum and slow down the data transfer. Because to measure an interfrequency cell, a client should synchronize to the new radio frequency band and measure its quality. During this period, the serving cell cannot send or receive data with the client. But if the client moves too fast, this policy can miss the good candidate cells without sending the feedback to the serving cell. Even if no intra-frequency cells exist, extra round trips are still needed to enable the interfrequency measurements, during which the client may have left the serving cell radio coverage and missed the opportunity for successful handover. The fundamental dilemma is that interfrequency measurements force the existing policies to balance the spectral efficiency and decision delay. Of course, the operators are aware of these network failures in extreme mobility. To mitigate them, their common practice is to adopt the proactive handover decision policies. They configure a negative radio quality threshold so that the client can trigger handovers before the neighboring cell is better than serving cell. In this way, the operator hopes to start handover early and mitigate the late handover failures we have just mentioned. However, this approach doesn't work because it causes policy conflicts and persistent loops between cells. When all cells adopt this policy, they will aggressively migrate the client to its neighboring cells. In this case, neighboring cells' handover conditions can be simultaneously satisfied. Then, even under invariant worse quality, the client will oscillate between cells frequently. Such policy conflict eventually offsets the operator's desire of failure mitigation because anyhow the client will move back to the weak cells. It's not good for both client and operator. Every handover has a cost. This loop accumulates cost and causes the client's network service disruption and causes signal store for the operators. Our study has shown that because of this practical strategy, policy conflicts in extreme mobility is 30 times more than those in static and low mobility scenarios. So how can we make the extreme mobility reliable? The fundamental solution is to get rid of the wireless-based mobility management because it will suffer from the dramatic wireless dynamics and the failure propagations to extreme mobility. To this end, this work relaxes the coupling between wireless and mobility management and shifts to this movement-based mobility management. Intuitively, the client movement decides its physical multipass and Doppler effect, which will affect the wireless quality. But compared to the wireless with short coherence time, the client movement is much slower and more predictable by nature. So it is more reliable to drive the extreme mobility management. So we propose RAM, the first movement-based reliable extreme mobility management. To track the client movement, RAM designs a signaling delay in the delay-Doppler domain on top of existing 4G and 5G physical layer. This signaling overlay exposes the client movement information and helps refine all phases of the mobility management. First, it stabilizes the signaling in execution with the OTFS modulation in the delay-Doppler domain. Then, to mitigate the failures from selective feedback, RAM parallelizes the feedback without reducing cell to explore. This is realized with a new crossband estimation in the delay-Doppler domain. Then, to eliminate policy conflicts and failures, RAM eliminates the multi-state decision policy with crossband estimation and enables easy to satisfy conditions for the conflict filter. We next show the key ideas behind RAM. The core of RAM is to track the client movement information in the delay-Doppler domain. To understand how it works, let's first look at some foundations of wireless communication. A wireless channel describes how radio signals from the sender propagates along multiple physical paths and combines at the receiver. It can be characterized in multiple ways. In 4G and 5G, they characterize the OFDM channel response as a function of time and carrier frequency. Instead, the delay-Doppler domain describes the wireless channel response in terms of the multipath geometry and Doppler shift between the client and the cell. Compared to time frequency domain, the delay-Doppler domain directly unveils the multipath geometry between the cell and the moving client. It's more stable than wireless quality because a variance relates to much slower path delay and Doppler changes. To this end, RAM places its signal traffic and reference signals in the delay-Doppler domain overlay. Intuitively, this will couple the signal transfer with a slowly varying multipath evolution, so signal traffic will experience more stable channel variations. To transmit the delay-Doppler signal traffic and reference signals, RAM leverages recent advances in OTFS modulation. The OTFS modulation can modulate the delay-Doppler signals to OFDM symbols using symplectic fast Fourier transform. In this way, the delay-Doppler signals are spread over the entire carrier frequencies and time slots. In this way, we can exploit the full time frequency diversity, which is more robust to combat signal loss and corruptions. Moreover, RAM also extends OTFS so that it allows the coexistence of delayed Doppler signal traffic and traditional OFDM data. For more details, please read our paper. With the delayed Doppler domain, RAM now can relax the handover's reliance on feedback for fast and satisfactory triggering. To achieve so, the key is to relax the unique dilemma in extreme mobility between the exploration with more feedback and exploration with fast feedback. Our key observation is that in reality, a base station usually operates multiple cells on a different frequency bands to improve the radio coverage and performance. Our data shows that 50% of cells share the same base station with another cell. So these cell signals traverse the same path from base station to client, so they experience similar channels in the delayed Doppler domain. Instead of measuring these cells sequentially, RAM leverages this shared multipath to parallelize the feedback with crossband estimation. For each base station, RAM measures one cell only and extracts the multipath profile. Then it maps this multipath profile to the other cells from the same base station so that it can estimate these cells' qualities without measurements. Here, I'm going to show you the high-level ideas of how it works. Let's consider one base station with two cells, cell 1 and cell 2. RAM first estimates cell 1's channel in the delay-Doppler domain. This is based on standard reference signals and procedures in the wireless communication. For each reference signal, we can estimate its delay-Doppler channel response, and then we can represent all reference signal delay-Doppler channel response as a matrix. Now, given cell 1's channel response matrix, our goal is to estimate cell 2's channel estimation matrix without measuring it. How can we do that? We find that we can decompose cell 1's channel estimation matrix into 3 submatrices: a delay orthogonal basis, a path attenuation diagonal, and a Doppler orthogonal basis. Note that the path delays and attenuations are independent of carrier frequencies. They are decided by the path length, light speed, and the materials. So they are identical for both cell 1 and cell 2. The Doppler shift is proportional to carrier frequency, so it differs between cell 1 and cell 2. But given cell 1's Doppler shift for each path, we can derive cell 2's Doppler shift based on their carrier frequency relationship. So if we could do this decomposition, we can reuse the path delays and attenuation matrix, derive cell 2's Doppler shift, and then reconstruct cell 2's channel estimation matrix. How to do that? We prove that this decomposition is equivalent to the classical singular value decomposition under some conditions. In reality, this condition can be mostly satisfied in the operational 4G and 5G network. So we can approximate this delay-Doppler channel estimation, delay-Doppler decomposition with singular value decomposition. To this end, RAM first runs singular value decomposition for cell 1's channel matrix. Then it derives cell 2's Doppler shift given the decomposition results, and then you can reconstruct cell 2's channel response matrix. For the complete algorithm proof, please read our paper. With the crossband estimation in the delay-Doppler domain, RAM lastly simplifies the handover decision to avoid multi-stage policy and conflicts. There are 3 main steps. First of all, for the interfrequency measurements, RAM bypasses the dilemma between spectral efficiency and decision latency. It replaces the multi-stage policy with crossband estimation. In this way, the client can estimate the interfrequency cells without measuring it. This saves the spectral cost and speeds up the decision. Moreover, with stabilized delay-Doppler signaling, RAM can eliminate many unnecessary configurations and events in today's policy. Please read our paper for more details. Lastly, with RAM, there's no need for the operator to adopt the proactive policy for failure mitigation. This helps prevent most policy conflicts in extreme mobility. Moreover, with RAM's policy simplification, we can achieve a much simpler rules for provable conflict freedom compared to the rules today. We have prototyped RAM in commodity software-defined radio and open source cellular protocol stack. We evaluated RAM with large-scale operational Chinese high-speed rail datasets and standard 4G and 5G multipath models. We compare RAM with the legacy 4G and 5G mobility management. Compared to a legacy solution today, RAM eliminates policy conflicts and reduces the failures by up to an order of magnitude. Now, even in extreme mobility, RAM still achieves comparable failure ratios to the static and low mobility scenarios. In achieving so, RAM still retains marginal system overhead. It reduces average feedback latency from 800 milliseconds to 200 milliseconds. So now it's fast enough for extreme mobility. Its crossband estimation has less than 2 dB estimation errors for more than 90% of measurements. This is sufficient for accurate handover decisions. Lastly, RAM greatly reduces the signal loss and corruptions in extreme mobility, so it's reliable enough for handover executions. In summary, this work shows that movement-based mobility management is more promising for reliable extreme mobility. We designed RAM, the first such solution in the delay-Doppler domain. RAM relaxes the coupling between the wireless and mobility to achieve parallel feedback, simplified policy, and stabilized signal. RAM is only the first step to demonstrate promise of its approach. Besides reliable extreme mobility, movement-based design in the delay-Doppler domain can also benefit many other tasks, such as trajectory tracking, channel prediction, geometry modeling, performance boosting, and many more. We wish for more community research efforts to explore them. Thanks for listening. I'm happy to take your questions.